Well, Unit 3 has been a long unit, and I just haven't figured out any way to make it shorter. There are several important concepts that we need to get familiar with. What I'm going to try to do now is to make sure that you take those important concepts away with you as we move on into Unit 4 and start talking about transport again. So what we set out to do, first of all, was to understand band bending and MOS structures and what we mean by accumulation, flat band, depletion, and inversion. Also, this critical band bending that is needed to create an inversion layer, 2 psi B. We then discussed the depletion approximation, which is widely used in many different contexts in semiconductor device work. So when we begin to deplete the semiconductor, this gives us accurate descriptions of the electric field and the width of this depletion region and things like that. Now, everything in the semiconductor depends on the band bending in the semiconductor and can be related to the surface potential. But the surface potential is controlled by the gate voltage. So we talked about how the gate voltage controls the surface potential. We talked about how to compute the gate voltage that gives us 2 psi B of band bending. That's the threshold voltage. We also talked about why flat band conditions generally don't occur when you apply 0 volts to the gate. That's because of a metal semiconductor work function difference. We then talked about the capacitance versus voltage characteristics of MOS capacitors, a widely used technique to learn a lot about the semiconductor insulator metal system. And then we talked about how the mobile charge, which is what we need for the next unit, the mobile charge carries the current in the MOSFET. We talked about how the mobile charge is related to the surface potential and how it's related to the gate voltage that produces that surface potential. And then we talked about 2D electrostatics. For small transistors, 2-dimensional or 3-dimensional electrostatics becomes more and more important, and these introduce effects that transistor designers have to deal with, and they've been doing it in more and more innovative ways as channel lengths have scaled to shorter and shorter dimensions. And the last thing was to explain how we can extend our virtual source model so that it not only describes the IV characteristics above threshold, but it also describes the IV characteristics below threshold. There are currents that flow below threshold. They're small leakage currents, but they're important in modern day systems. So Unit 3 was all about the charge and how it's related to voltages that we apply to the gate and drain. Okay, so first thing was one-dimensional electrostatics. So here we have an MOS system. We have a semiconductor, a p-type that we assume is infinitely thick. We have a thin oxide, and we have a metal electrode. The VG prime means that this is an ideal case where the Fermi level in the metal and the Fermi level in the semiconductor just happen to line up at 0 volts applied to the gate. All right, that rarely occurs. But conceptually, it's a simplifying way to deduce what happens, and we can fix it up later. If we apply a negative voltage to the gate, we induce a negative potential in the semiconductor. A negative potential raises the energies in the semiconductor and pulls the bands up. And you can see here that that negative voltage on the gate is going to attract positive holes. They're going to pile up near the interface. Positive holes, majority carriers, accumulate near the oxide silicon interface. On the other hand, if we apply a positive voltage to the gate, that induces a positive potential in the semiconductor. Positive potentials pull the energies down. The positive voltage on the gate pushes the holes away, and you can see from the energy bands in the semiconductor that we have fewer holes near the surface. We say that the surface is depleted. If we continue to increase the positive voltage, we'll pull the conduction band so close to the Fermi level that we invert the semiconductor and get a high density of inversion layer electrons. Well, that allows us to qualitatively understand how the charge in the semiconductor depends on the surface potential. Negative surface potential causes majority carriers to pile up, majority carrier holes in a p-type semiconductor. So we quickly get a high density of majority carrier holes. A positive surface potential depletes the p-type semiconductor. The charge increases as the square root of surface potential. But then if we bend the bands far enough, the semiconductor inverts and the charge builds up exponentially. That occurs at a critical band bending of 2 psi b. The flat band condition is when the bands are flat and there's no charge in the semiconductor, so that occurs between accumulation and depletion. Now, in depletion, we can solve the Poisson equation fairly easily. This is a widely used simplification. It starts by saying divergence D is equal to rho, and then we can easily compute the width of this depletion region, W sub D, the electric field, that's a surface, E sub S. We can also compute the charge in the depletion layer. So we get some very useful quantities that we need to analyze transistors and MOS capacitors. But everything depends on the surface potential. Everything that happens in the semiconductor depends on the potential in the semiconductor. But it's the voltage on the gate that produces that surface potential. So we talked about how we relate the gate voltage to the surface potential. We simply used Kirchhoff's voltage law. Voltages add up. The voltage in the bulk semiconductor is 0. The voltage at the surface of the semiconductor is psi sub s. That's the voltage drop across the semiconductor. The voltage drop across the oxide is delta V ox. And the two have to add up to the gate voltage. Okay. And we showed that if we do that, we get this fairly simple expression that relates to gate voltage and surface potential. Of course, we need to compute the charge in the semiconductor, so we need to know how the charge in the semiconductor varies with surface potential. Then we can, given a surface potential, we can compute the charge in the semiconductor, and then we can figure out the gate voltage that produced that surface potential. Just remember that the oxide capacitance here is just the dielectric constant of the oxide divided by its thickness. Now, this is not a very complicated expression, but it involves, under depletion conditions, it involves a square root of the surface potential in the depletion charge. It makes it a little difficult to deal with. We also talked about an approximate way to deduce the surface potential from the gate voltage by thinking of this system as 2 capacitors in series. Now, it's an oxide capacitance and it's a semiconductor or depletion capacitance if we're in depletion. That depletion capacitance is voltage dependent. So this is really a little bit complicated. But if we assume that we can just use an average surface potential, then we can treat it as 2 capacitors in series. We can relate the voltage between those 2 capacitors to the voltage we apply in the gate by voltage division in 2 capacitors in series. And what we find is that the surface potential is the gate voltage, some fraction of the gate voltage. And that fraction is determined by this important parameter m, which is always greater than or equal to 1. Now, if we just do a calculation and plot surface potential versus gate voltage, we'll get a plot that looks like this. As long as the bands have not bent too much, we're depleting the semiconductor, and the bands bend significantly when we change the gate voltage. Right? The fraction is less than 1 because not all of the gate voltage gets in to the semiconductor. That's that parameter m that we just mentioned. But there's a significant variation of the surface potential with the gate voltage. Things change when we bend the bands by 2 psi b and create an inversion layer. That occurs at the gate threshold voltage when the bands are bent by 2 psi b. So we can compute that threshold voltage, and that's an important transistor parameter. Now, when we continue to apply gate voltage and bend the bands more, what we find is that it is very hard now to bend the bands much beyond 2 psi b. We'll bend them a little bit, a few kT, but it is hard, no matter how large the gate voltage is, to bend them by very much. That's because the charge is piling up exponentially, the electron charge in the inversion layer. The volt drop across the oxide, which is charge in the semiconductor divided by oxide capacitance, is getting very big. All of this added gate voltage just increases the volt drop across the oxide and doesn't do much with the semiconductor. So we can bend the bands a few kT, but not very much. It gets hard to bend the bands. Now, we also discussed some non-ideal characteristics. VG prime means we're talking about an ideal MOSFET. What happens in a non-ideal MOSFET? Well, one of the most important things is that the metal and the semiconductor have different work functions. You'll recall that the work function is the energy that it takes to move an electron from the Fermi level out into the vacuum. So depending on the metal, that'll have some numerical value. Well, there's a work function for the semiconductor too. And the chances are those two work functions are not going to be the same. When we put this metal insulator and semiconductor together and we're in equilibrium, there has to be one Fermi level constant everywhere. You know, how is that going to happen? Well, that happens because a positive potential develops on this gate, a built-in potential there, even in equilibrium, which lowers the energies in the metal gate, pulls this Fermi level down so that it aligns with the Fermi level in the semiconductor. So that metal semiconductor work function difference, capital phi sub ms in joules or expressed in electron volts, is important to know. We can also express it as small phi sub ms in units of volts. And what we conclude is that a positive voltage equal to minus phi ms must develop in order to pull the Fermi level in the metal down and align the Fermi levels in equilibrium. Right? So, you know, what that means is that when we apply VG equals 0, we already have a built-in voltage on the gate before we've applied an external voltage. So the bands are already bent. And typically for a p-type semiconductor, we'll find that the semiconductor is depleted with no voltage applied to the gate. Now, something else can occur. There is often a sheet of charge at the oxide silicon interface. In the SiO2 silicon system, that tends to be a positive sheet located very near this interface. And we have to account for that too. So the actual gate voltage is shifted from the ideal gate voltage by the flat band voltage, which no longer appears at zero gate voltage. The flat band voltage depends on the metal semiconductor work function difference, but this sheet charge will also affect the volt drop across the oxide and affect the flat band voltage as well. But that's simple to account for. If we know the magnitude of that charge in coulombs per square centimeter, it simply affects the flat band voltage. Okay. So, typical MOS capacitors have band bending before we apply any voltage to the gate. We also talked about capacitance versus voltage measurements, because this is a powerful tool for probing MOS structures and understanding physical things about them. So in this case, we have an MOS capacitor, a metal gate, an insulating layer, and a semiconductor. We apply a DC bias, we measure the AC small signal current that flows in, and we deduce the capacitance as we vary the DC bias. So we get a small signal capacitance versus DC bias characteristic. For a p-type semiconductor, ideally it would look something like this. Real structures have some finite negative, typically flat band voltage for a p-type semiconductor. So it is simply shifted. And we talked about how we interpret this. If the gate voltage is less than the flat band voltage, we accumulate the semiconductor, holes pile up near the oxide silicon interface, we have electrons on the metal gate, we have two metallic conductors surrounding the oxide, so the capacitance is just the capacitance of the oxide. As we apply a voltage that is more positive than the flat band voltage, we deplete the semiconductor. It's now as though we have a thicker capacitor with two insulators inside of it. The capacitance drops, and it continues to drop until the semiconductor inverts. When the semiconductor inverts, we get a highly conductive layer of mobile electrons right below the oxide. This might look very similar to the accumulation case. Metallic-like plates surrounding an oxide. Why don't we get the oxide capacitance? Well, the reason is, if we do this measurement at high frequencies, these charges are there, but they cannot follow the AC frequency. And it turns out it doesn't take a very high AC frequency for that to happen. So as that gate voltage goes up and down at some frequency, and we ask for more inversion layer electrons, it takes a while to generate them. So they can't follow the signal. It's as though they are not there for the AC signal. So we measure the high frequency capacitance. Under low frequencies, those charges can follow the signal. So we measure the low frequency capacitance, and the capacitance in inversion then is very close to the accumulation capacitance. If we were to measure this capacitance in a MOSFET, we would measure the low frequency capacitance, because the source and the drain provide sources of electrons that can quickly go in and out and follow these AC signals, even at high frequencies. Okay, what an important part of the discussion of this unit is the mobile charge. It's the mobile charge that carries the current in a MOSFET, and that is really what we're after, to understand this mobile charge. The mobile charge in coulombs per square centimeter, which we get by integrating the mobile charge per cubic centimeter into the depth of the semiconductor. Under inversion conditions, most of that is piled up at the oxide-silicon interface. And we can expect that it's going to vary exponentially with surface potential. And in fact, we worked this out, and we showed that it does vary exponentially with surface potential. There is a factor of 2 in a bulk semiconductor above threshold, but it still varies strongly, exponentially with surface potential. In an ultra-thin body, fully depleted channel, which is more typical of the modern highest performance transistors, it varies exponentially with surface potential above and below threshold. So if we then move on to what gate voltage produced that surface potential, ultimately we really want to relate the mobile charge that's responsible for the drain current to the gate voltage that we put on the terminal. Well, in both cases, for the ultra-thin, fully depleted structures and for the bulk MOS structures, below threshold, the mobile charge is very small, but it's there and it carries the current, and it goes exponentially as VGS minus VT. In a bulk structure, there'll be a factor M. It is a little bit bigger than 1. That'll be in that expression. Okay. The fact that M is 1 is really very useful and helpful for ultra-thin body, fully depleted structures, because M is always a little bit bigger than 1 for a bulk structure. Okay, so 2D electrostatics complicate the analysis of semiconductor devices and the design of MOSFETs. So what they do is they introduce some non-idealities, things like dibble. One of the things we notice in dibble, what dibble does is if there is some arbitrary current, we say, okay, now that the device is on, it takes a certain voltage, a certain gate voltage to reach that current. It takes a lower gate voltage to reach that current when we have a high voltage on the drain. The threshold voltage decreases as the drain voltage increases. That's not a desirable feature for a transistor. We want the threshold voltage to be fixed. Right? Now also, the threshold voltage will decrease at a given drain voltage if we shrink the channel length. That's also not a desirable feature to have. We don't want different channel length transistors to have different threshold voltages. It complicates life for circuit designers. Now, dibble also increases. Not just, dibble and these differences in threshold voltages are really the same thing. As the channel length shrinks, at a fixed drain voltage, the dibble will also increase. Now things can get very bad. The subthreshold swing may also increase as the drain voltage increases. Even in a fully depleted ultra-thin body structure, that's not a desirable characteristic. The subthreshold swing may increase as the channel length gets smaller. So things get worse and worse as the channel length shrink. That's not a desirable feature. And in severe cases, the device might punch through. And that means that even if we don't apply a voltage to the gate, significant amounts of current may be flowing. That's not a desirable feature for a transistor. Now, 2D electrostatics are also responsible for the finite output resistance. In an ideal MOSFET, or in a long channel MOSFET, the current would be independent of drain voltage in the saturated regime. In a real MOSFET, 2D electrostatics make sure that the current is affected by the drain voltage. The output resistance gets lower and lower as the channel length gets shorter and shorter. And we can, sort of understand what's going on in an energy band diagram again. So under high VDS, we pull the energy band diagram down. In a well-designed transistor, the barrier between the source and the channel is mostly controlled by the gate, but not entirely. So the drain will pull it down a little bit and increase the current. That lowers the threshold voltage because now we need a smaller gate voltage to push the barrier down and turn the device on. So that's a consequence of the 2D fields that are reaching through and pulling down this potential barrier at the source. So lowering this barrier increases the current and reduces the threshold voltage. Increasing the drain voltage also will lower the barrier. So either shrinking the channel length or increasing the drain voltage, both of them can lead to this effect. So a lot of modern transistor design is all about controlling these 2- and 3-dimensional electrostatic effects. We would like to make sure that the electric field lines that emanate from the positive voltage on the drain, terminate in the bulk or terminate on the metal electrode and the gate, and do not reach through all the way to the source, pull down the barrier and pull electrons out of the source. When that happens, it's catastrophic. The device has punched through. So a key factor is this geometric screening length, which is sort of the distance over which the electric fields from the drain can reach and have influence. We want that to be shorter than the channel length. And this is a reason that modern very short channel transistors have gone to more sophisticated structures like FinFETs, in which you try to wrap the gate around the channel to as much as you can to protect the channel, the potential barrier near the source from the influence of the electric field lines that emanate from the drain. So if we've done our transistor design properly, we would have what we call a well-tempered MOSFET, a term introduced by my colleague Dimitri Antoniadis at MIT. In a well-tempered MOSFET, this simple one-dimensional expression that we have for the charge, mobile charge as a function of gate voltage, holds at the top of the barrier. And you might ask, how can that happen in such a complicated small device with all of these two-dimensional effects? Well, that's the task of the transistor designer. That's why people go to structures like FinFETs, to make this happen. So we know the charge at the top of the barrier. There is a little bit of dibble, there always is, but you try to make it as small as you possibly can. And we try to make sure that the subthreshold swing parameter M doesn't increase as we change the drain voltage. So there is a region near the source that is mostly controlled by the voltage on the gate and weakly controlled by the voltage on the drain. That's a well-designed transistor. If we increase the drain voltage, most of the voltage drop will occur near the drain. This region near the top of the potential energy barrier, which controls the current, how much current can get out of the source and flow to the drain, that is mostly unaffected then by increases in the drain voltage. That's why the current saturates. Well, to end up Unit 4, we revisited our virtual source model. One of the things that we did is to extend it by no longer assuming that there was no charge when the gate voltage was below threshold. We could extend it with an empirical expression that correctly gives us, or approximately gives us, the right mobile charge below threshold and the correct mobile charge above threshold. That introduced a couple more empirical parameters that don't change very much from transistor to transistor. So with that, we have still a small number of parameters that we can fit to measure data, and these parameters, almost all of them, except maybe for this parameter alpha and beta, have a very clear physical significance. They're not simply empirical fudge factors. Now, in this course, in this unit, we learned how to express the mobile charge as a function of gate to source voltage both below and above threshold. That means that we can compute the current both below and above threshold. Since current is charge times velocity, we know that the charge varies exponentially with Vg minus Vt below threshold. We know that the current will as well. And we have an expression for the current as a function of gate voltage below threshold now. That allowed us to deduce the subthreshold swing, and we found that it was 2.3 times this numerical factor m, which is always greater than or equal to 1, times kT over Q. If m is 1, that's 60 millivolts per decade. That's a fundamental limit for the way that this barrier-controlled device operates. And the transistor designer tries to make m as close as possible to 1 as we can. Two-dimensional electrostatics degrade m. Fully depleted structures help m. The transistor designer does the best job that she or he can do to make m as close to 1 as possible. Now, subthreshold swing is important because it determines the lowest power supply voltage that we can use. We would like to go from off to on conditions with the smallest possible power supply voltage. Because remember, power dissipation goes as voltage squared, the dynamic power. The lower the voltage that we can use, the less power we dissipate, the more transistors we can put on a chip. And that is why, over the last several decades, power supply voltages steadily decreased until recently we've lowered them about as low as we can go in a silicon transistor. Okay, it has been a long unit. Spend some time in getting familiar with these concepts. I've tried to explain them as simply and clearly as I can. There are a few important takeaways that if you understand those, we know the charge part of the current equation. Now we can move on to Unit 4 and use that understanding to compute the IV characteristics of nanoscale devices. I'll see you in Unit 4.